Over the past sessions, we've explored the history, economics, and overall development of the Canary Wharf Crossrail station. However, there is still more to be said about the top-down construction method, and today, we'll be taking a closer look at that. Now begins the full-scale implementation of the top-down construction method. Plunge columns are driven into the locations where the building's reinforced concrete columns will eventually be placed. These plunge columns temporarily support the load of the upper slabs during the top-down process. Due to the nature of the method, where slabs are constructed from the top-down downward while excavation proceeds below, immediate structural support is required during each stage, and the plunge columns serve this critical role. A total of 30 were installed on the site, spaced at 12-meter intervals along the center line. The columns were not aligned in a perfectly straight line. At future more hole locations, 2 columns were placed side by side at 3-meter intervals. Once excavation is completed down to the lowest level and the permanent columns are installed, the structural role of these plunge columns is partially transferred. They are then integrated with the superstructure and used as part of the permanent structural system. At the lowest level, an additional 71 tension piles are installed beneath the station box floor to support the structure. Tension piles are a type of pile foundation used to resist uplift forces that might otherwise cause it to be extracted from the ground. These piles provide additional resistance as a permanent structural measure against rising groundwater levels. Let's take a closer look at the construction process, starting from the sublevel 3, which is closest to drain dock bed. First, the ground is excavated to a depth of approximately 2 meters. Then, temporary supports are installed in intervals of about 1.5 meters to support the formwork that will be placed afterward. In areas designated for mole holes, spaces reserved for the vertical transportation of materials and workers, as well as for future escalators and elevators, plunge columns are interrupted and cannot connect directly to the beams. To address this issue, temporary columns were installed within these areas to provide additional structural support. In addition, reinforcement beams were constructed around the mole hole openings between the piles and the plunge columns to enhance stability. On top of the formwork, reinforcement bars for the beams are placed first, followed by the reinforcement for the slab. One important point to note is that reinforcement and concrete pouring are carried out except the mole hole areas. At the sublevel 3, a total of 23 mole holes were installed. This includes 4 ventilation shafts located at each end of the floor, 1 stair core, 1 elevator core, 1 escalator opening, and several additional openings for escalators and elevators, providing access to the retail area. For the concrete placement of the slab, the work was divided into 9 separate sections organized around the mole holes. Due to the nature of the top-down construction method, the upper slabs are built first, followed by the lower slabs. At this stage, it was impossible for the plunge columns alone to support the upper slabs, which span up to 30 meters in width. Therefore, additional support was required to provide basic connections between the plunge columns. For this purpose, the existing second pile wire and sheet pile wire on either side were utilized. During the construction of the sublevel 3 slab, the second pile wire was located below the slab level, naturally providing support at one edge of the slab. Support on the opposite edge was provided by the sheet pile wire. The excavation for sublevel 4 was carried out simultaneously. Excavation began beneath the formwork through the mole holes. Through the mole holes, workers and materials needed for excavation were moved downward. After the excavation for sublevel 4 was completed, the process of constructing the sublevel 4 slab began, just like the sublevel 3 slab. There were a total of 21 mole holes in sublevel 4. Rebar was placed except in those areas, and to support the slab edges, second piles were connected on the south side and the gecko piles on the north side. After that, concrete was poured into the formwork. After the sublevel 4 slab was completed, excavation was carried out for the sublevel 6 construction. Likewise, excavation and slab construction were carried out, while column and wall reinforcement work continued on sublevel 4 and 3 to effectively shorten the construction period. The connection between the slab and the geek and pile wall was constructed using a tenon groove system. The construction process followed a specific sequence. Inside the pre-cut groove, a waterproof membrane and steel anchors were inserted. Next, formwork was installed and reinforcement was placed. During this stage, the slab and beams were reinforced simultaneously. When the concrete was poured, it filled the grooves, physically locking the slab tenon into the wall and creating a mechanical interlock. The slab and beams were cast together as a single operation, ensuring a monolithic structure without additional cold joints. In the case of Canary Wharf Station, the platform spans a wide area horizontally, making lateral bending resistance of the slab particularly important. Therefore, the beams running along the flange columns were designed to be thicker and stronger than the beams simply connecting flange columns to the adjacent wall systems. This design ensured sufficient structural capacity to resist bending and deflection across the entire structure. Proper connection between the slab reinforcement and the columns and internal walls that would be built later is essential. For this purpose, mechanical couplers were used. These couplers were pre-installed at the locations where columns and walls would later be erected. Vertical reinforcement bars were either threaded or inserted into these couplers to ensure structural continuity. It is important to note that sublevel 6 was constructed before sublevel 5. The subway runs at the lowest level of the station, sublevel 6, so the TBM also had to pass through sublevel 6. The diameter of the TBM used in the Crossrail project was 7.1 meters. If sublevel 5 was constructed first, the TBM would either have to break through that level while passing or might not be able to enter at all. Therefore, instead of building sublevel 5 first, sublevel 6 was constructed to secure space for the TBM. In fact, the floor-to-floor height difference between the sublevel 4 slab and sublevel 6 slab is 10.1 meters, and by removing sublevel 5 in between, a vertical clearance sufficient for the 7-meter TBM to pass was secured. In addition, unlike other floors, the slab at sublevel 6, which is the deepest part of the Canary Wharf station, has slopes at both ends. Since earth pressure and water pressure act horizontally in the underground, the slab was sloped to disperse these forces. After the TBM passed and the construction of sublevel 5 was completed, all the slabs of our station were constructed. In the middle of this process, to form the wall, SCL, which means concrete lined, was applied by spraying concrete along the excavation surface. Simply put, it is a method of forming a wall by installing a reinforcement mesh on the excavation surface and then spraying concrete.